Hello students, hope you are fit and fine in this pandemic situation. So in this 5th paper of TYBSC, we are going to learn what is thermal sensor in 5th paper of TYBSC physics. So let us begin with what is the meaning of thermal sensor. Before that, these thermal sensors are used for measurement of the temperature. So let us see what is this temperature. So therefore, let us see what is the definition of temperature, and we have written that it is the manifestation of average thermal energy per molecule. We know that there are 3 basic states of matter, that is solid, liquid and gas. So when there is solid, then atoms are very rigid with respect to each other. When we supply them energy, then that bonds get break and they will convert into the liquid. Now once the atoms are enter in this liquid state, then molecules are trying to slide with respect to each other. Again, when we give them more and more energy, then in that case this liquid is converted into the gaseous state. So here we have seen how with respect to change in energy, states are getting changed. So over here the definition of temperature we are put forth in terms of how there is variation in thermal energy per molecule. So these molecules are playing very important role when we are going to see the definition of temperature, and therefore we have written the definition in terms of average thermal energy per molecule. Before finding this temperature sensor, there are 2 basic important units, and those units or those temperature scale we have written over here as absolute temperature scale and relative temperature scale. For this absolute temperature scale, it is the special unit in which we assign 0 thermal energy, and there is no vibration or no molecular vibration. So it means that those temperature scales are having 0 thermal energy at which molecules are not vibrating. When in case of 0 thermal energy, the atoms are not vibrating. When we supply them energy, then atoms are start to vibrate about their equilibrium position. So over here we have assigned 0 of this particular unit scale at which there is no any molecular vibration. So this is the definition of absolute temperature scale. For the same, we have taken example of those as degree Kelvin and degree Rankine, and they are related by this way. So degree Rankine will equal to 9/5 multiplied by degree or temperature in degree Kelvin. So these 2, that is degree Kelvin and degree Rankine, are collectively said to be as absolute temperature scale, and those units are having 0 thermal energy and at which there is no any molecular vibration. So those are, that is degree Kelvin and degree Rankine is said to be as absolute temperature scale. So from that one can say that at 0 degree Kelvin as well as at 0 degree Rankine, the molecules are not showing any vibration. This is the characteristics of absolute temperature scale. On the contrary, in case of relative temperature scale, their 0 has been little bit shifted in such a way that their relation, that is temperature in degree Fahrenheit, will equal to 9/5 into temperature in degree Celsius plus 32. So in earlier case there was 0 thermal energy at no molecular vibration, while over here even if there is 0 temperature scale, still molecules are not stationary. So this is the basic difference between absolute and relative temperature scale. So here we have taken as an example temperature in degree Fahrenheit and temperature in degree Celsius. So collectively degree Fahrenheit and degree Celsius are said to be as relative temperature scale. So these were 2 units or temperature scale that we are going to use in latter case. For the same, if we know that if molecules are stationary at absolute temperature, they are not showing any vibration, then for the same one can say that if we vary temperature, then speed of molecule is getting changed. So therefore we have written 3 by 2 kT will equal to 1/2 mVth square, where this right hand side will indicate kinetic energy and left hand side it is 3 by 2 k multiplied by T, where this k is the Boltzmann constant, and therefore from that this Vth we will receive at square root of 3 kT upon m, where this Vth will give us speed of molecule, and this equation will enable to us that how variation of temperature will give us how speed can be changes. So this is the unit, or this is the way by which one can represent the thermal energy, or it correlates speed with respect to the temperature. Now there are different types of sensor for the measurement of temperature, like thermistor, thermocouple, resistance temperature detector, and many more. So let us begin with this RTD, that is resistance temperature detector. So this resistance temperature detector is one of the scale in which we are taking the advantages of how variation of resistance is getting changed of metal with respect to the temperature. So for the same we have taken as an example of how this variation of resistance of metal will get changed. For the same we have drawn a diagram in which along y-axis we have taken energy, and we have shown that in case of metals only, CB, that is conduction band, and valence band, they are overlapped. As a result of that we have written there is no any band gap. So one can say from that is at room temperature many more electrons are present. Electron means free electron or conduction electrons are present even at room temperature, or there is no any resistance offered by metal to the flow or to the motion of free electron or conduction electron. So therefore we have shown there is no any EG or band gap to the flow of motion of electron. So if there is many more number of electron, then let us see how this variation will get changed with respect to change in temperature. So for the same, if we increase temperature now, then what will happen? That the atoms or the molecules will start to vibrate about their equilibrium position. Now as we know that even at room temperature free electrons are moving from one point to another point within a given metal. So if that electron gets collide with respect to vibrating atom, then resistance will be offered. Now if we increase temperature, then in that case there will be vibration of an atom will increase. As a result of that, these electrons they may get collide with respect to vibrating atoms. During their collision, the energy of electron will get reduced. As a result of that, resistance will be offered. So from that, we can say generally that if we increase temperature, then vibration of atom will increase. If vibration will increase, then collision also increase. If collision will increase, then resistance also increases. So in short, in case of all the types of metal, even if they are characterized by many more conduction electron or free electron, still with respect to increase in temperature, if many more atoms are vibrating, then resistance will get increased with respect to increase in temperature. So we are going to take these advantages that if there is change in resistance with respect to change in temperature, can we see or can we make such sensor? So answer to this question is yes. And this RTD is consisting of metal, or in this RTD we are going to see how this metallic resistance is varying with respect to temperature and how one can use this for measurement of temperature. For the same, we have drawn the diagram which represent how resistance is varying with respect to change in temperature. And there are shown two examples, that is nickel and platinum. For the case of nickel, you will able to see that the span is less. So if we change temperature from 0 to approximately equal to 250 degrees Celsius, then in that case its resistance is getting changed. while in the case of platinum, its resistance is little bit less vary as compared to nickel. So from these and from earlier explanation, we can say that metallic resistance varies linearly with respect to the temperature, and therefore these advantages we are going to take for measurement of temperature. Now in general, we know that resistance for the case of metals can be represented by this simple expression that we may have learned, that is R will equal to rho L by A, where this rho is resistivity expressed in ohm meter, L is length, A is area of cross section, and R is resistance. So from this expression you will able to notice that which quantity is getting changed with respect to increase in temperature, so that resistance getting changed. So over here one can say that if resistivity is getting changed with respect to temperature, then this resistivity is playing important role. So we have written this R of T at any unknown temperature upon R of 25 degrees Celsius will equal to rho T upon rho of 25 degrees Celsius. So if we know rho T, that is resistivity at unknown temperature, if we know rho at 25 degrees Celsius, that is known to us. If we know R of 25 degrees Celsius, then RT, that is resistance at unknown temperature, can be determined. Now this RTD, as I told you, will consist of metals, and this resistance temperature detector are working on this principle. And there are two better approximation. The first one is linear and second one is the quadratic. For the same, we are going to see what is this linear approximation, and this linear approximation is working only in between the range of 0 to that of 100 degrees Celsius only, because the linearity, that is how variation of resistance with temperature, that is very small segment. So therefore this approximation or linear approximation is the limited application of this RTD. And let us see how this resistance and temperature are related under the heading of linear approximation. For linear approximation, RT will equal to RT0 and in bracket 1 plus alpha 0 in bracket T minus T0. So this RT0 we have written, it is the temperature at which resistance is known to us, and this alpha 0 is the constant and it is linear fractional change with temperature. If we change the temperature, how resistance is getting changed, that is represented by this alpha 0 over here, and this alpha 0 will have unit per degree Celsius or per degree Kelvin. So this RT is equal to RT0 in bracket 1 plus alpha T minus T0 is used for the linear approximation or for shorter span of the temperature over here. The remaining, that is quadratic approximation part of this RTD, we will see in the next lecture.